right, take two, perfect. Let's all right, let's get started. Terribly sorry about that, but at least we're up and running now. Okay, in the year 1587, we had the Pope Sixtus V, who introduced quite an interesting new function or new job in at the Vatican. He introduced something called the Advocatus Diaboli, which is the devil's advocate in English, which is basically a position where somebody could have the last-minute objection if somebody else was on the road to sainthood and that person didn't agree to it. And I think we've had a little bit of that road to sainthood with microservices for the last few years, and this talk will hopefully provide some food for thought on maybe questioning some of that. So let's get started. On our road, when we create code, it all basically starts in our head, and then eventually in our IDE we type in some source code, and then we'll compile that, and eventually we'll run it on the physical hardware on the CPU. So that's basically the direction that the code flows from head to machine. And as we move beyond toy projects, as we move towards more substantial code bases, where does this system start to break down? Where is the code size becoming a problem? Well, it turns out that it's very clearly on our end of things. Why? Because as code starts to grow, the machine doesn't really have a problem to compile a whole many more classes or execute many more instructions. It's more on our side that we start to have trouble understanding. Because if we kind of look at the read-write ratio that we have with our code, we actually spent a lot more time trying to understand exactly what this portion of the application is doing, how it is actually functioning, and how the new requirements that I have could actually be shoehorned or integrated in there. And then finally, once we're convinced of how to make the change, we do actually implement it. So we have a much higher read ratio than a reads part than a writes. So we should, of course, if we want to improve this over time, start looking at how to optimize the read part. So how do we do that in practice? We add structure to our code by, we raise the abstraction level, we try to reduce the cognitive load to make things easier to understand. We're really trying to see the forest through the trees. How do we do that? What kind of tools do we have at our disposal? We have methods, and once we have a bunch of methods that have accumulated some code, we can group them together in classes, and these classes can then be grouped together logically in packages, and packages can be brought together in modules, and modules can be brought together in applications. So we really have a whole bunch of tools at our disposal to kind of raise that abstraction level and reduce the cognitive load. And what we really have here is our software architecture, which is nothing else than the relationship and the interactions between these different tools that we put in there. And if we look at the architecture styles that have been very popular for the last few years, or at least the ones we heard the most of, it's pretty much been these two, where we've had the monolith on the one end and microservices on the other, and these are some good visual representations of those. But if we were to judge by the conference agendas from the last 3 or 4 years, we probably would have slightly different images for those. It would be closer to something like this, where we have a quite negative view on the monolith, and we have a very hip microservices side. Why? Because microservices, of course, have been actively pushed by a good number of companies that are very dominant in our tech industry. I think the Amazons, the Googles, the Netflix, the Twitters of our world, they've contributed a lot to the open source ecosystem as well in terms of projects and tooling being able to support such a microservices setting as well. So actually, it's been working very well for them as well. So that's kind of good to hear. But the other thing that's interesting is this very interesting quote. If you fetishize about and cargo cult the infrastructure required by companies with literally 10,000 times your traffic, you will not have fun. Now, let's see. What does this really mean? The order of magnitude of certain companies. Let's have a look, for example, at the Amazon jobs page. So this is just, you can type it in your browser, Amazon the jobs, and let's see how big they really are and what kind of open positions there. So if we kind of look, we see that they have about 6,400 open positions. So you'll say, well, Axel, of course, because they have a lot of people working warehouses and doing delivery and all kinds of jobs like that. So let's have a look. Let's scroll down a little. And what do we see? Oh no, there's a filter. These 6,400 positions, it's only for AWS. But you can tell, well, Axel, AWS, you've got lots of salespeople, you've got lots of managers and overhead, so let's dig a little bit deeper. Oh, we've got software development with 1,700 positions, so we've got solution architects and operations, and we've got about 3,800 open positions at AWS right now. Now take a step back in your head and think about your company. How many developers, architects are you actually seeking at on the market right now? Not the ones that you have, the ones that you want to add on top of your existing team. Is it 3,800? 380? 38? 3? Think about it. And then think where you stand in terms of size with your company and capacity that you have available to develop software systems compared to some of those very, very large companies pushing those tools on the microservices side of things. So I think the first thing we should do to kind of start and rectify this and take away the loaded connotations is to start using more objective terms, where instead of monolith and microservices, we should maybe call them integrated systems and distributed systems, where we have something that is fully integrated in terms of deployment and the other alternative, something distributed in terms of deployment. But distributed, we heard that somewhere, didn't we? What did Martin Fowler have to say about it? All right, the first law of distributed object design, don't distribute your objects. Well, maybe there's something about that. So let's see, let's kind of compare what monoliths and microservices have to offer. So monoliths, quite nice. We've got one simple artifact that is nice and easy. On the microservices side, we've got a bunch of different artifacts. On the other hand, on the monoliths, we have entanglement risk, which has been part of the reason why it's been getting a bad reputation, versus the microservices side, where we have very clear units that are nicely separated. This is actually quite a good thing. On the other hand, when it comes to communication between those parts, on the monolith, we've got nice, simple method calls versus unreliable networks and a whole bunch of infrastructure that we need to put around that to compensate for it on the microservices side, so that on the monolith side, we have the guarantee that if one part is available, all parts are available. On the microservices side, we need to start introducing additional infrastructure like service discovery and internal load balancers and circuit breakers to kind of compensate for the fact that we have a network in there all of a sudden. The good thing about the monolith is we have everything in our IDE together, and our IDEs are very good these days. So we can just use the refactoring functionality of the IDE, and it will nicely find all the references to a method, and it will rename it everywhere if we need to. If we've got a REST API in a service, it is much harder first to find out who's actually using it, and then gradually transitioning all the clients to some new version of that service. The monolith, in terms of scaling, doesn't offer a lot of possibilities. We just scale it all up or all down, versus microservices, where we've got all these individual knobs that we can turn, so that's actually quite powerful to be able to scale individual pieces separately from one another. The monolith, in terms of persistence, will typically have one database where it will be storing everything. Microservices have basically a choice per service, assuming that you don't do database level integration, which you shouldn't, so that each microservice can then pick the most appropriate type of persistence technology it requires, which is a good thing. On the other hand, a good thing about having one database is having the guarantee that if you make a change on one end and you need to make a change on the other end at the same time, that it actually happens at the same time, transactions, versus the microservices side, where you still need those guarantees, but the system isn't really helping you anymore, so you need to start compensating in software for the lack of transactions across those different services. So that creates a bunch of additional work that is on your shoulders there. The monolith by definition, will run on a single platform like the JVM or Node or what you choose there. The microservices, as they have a network in between, do not have any such constraints. So if one service should be running on the JVM because it's the most appropriate technology for that, it can do it. And if another one should run on Node, it can do that too. Of course, risk, if you run it all together on the JVM, for example, we have the risk of jar hell with dependencies, transitive dependencies that maybe have conflicting versions, versus on the microservices side, no such problem. Again, we can have vastly different versions of the same library being used by individual services without running into these issues. In terms of division of labor, we have a limited set of options to parallelize work on the monolith side versus the microservices where we really have the option to have a team per service and to be able to scale much higher in terms of capacity of people that we have available there. So if we were to synthesize the two things that we have there, we can really see that it's not really black and white, like there is advantages and disadvantages to both. And monoliths are very useful at the low end, where you can have a small team producing simple applications and being very, very successful and productive at that without any of the overhead of microservices. On the other hand, microservices are essential at the high end, where you want to have strong division of labor, you want to produce very large applications, you want to support large companies. I think those are very important things at the high end. But is there maybe room for something in the middle? Does it have to be so far apart? So yes, there is. It's called distributed monoliths. It's fantastic. No, just kidding. Don't try this at home. There is a much better solution to combine the advantages of both, where we can take the simplicity in terms of deployment and physical architecture of the monolith and combine it with the logical architecture of microservices and have something called a modular monolith. And in fact, it provides a lot of advantages and provides so many that I actually think we should call it Majestic Modular Monolith instead. So let's see why that is. When we talk about monoliths and their bad reputation, let's say, very often it's kind of easy to be a bit unfair in the criticism and say that they look somewhat like that if you look at the code behind the scenes. But that's not really true. Most monoliths are much closer to this, where you have at least some kind of structure that you can recognize in there. It's maybe not perfect, maybe slightly leaky, but you do have some kind of structure there. Because the layered architecture, as we know it, is really very, very pervasive, where you have your classical controllers, your services, your repositories, your database, and basically you kind of only go down, so controllers can only talk to services, they talk to repositories and to database. And then you maybe have a model layer, a domain model that all of them can access. So this is very, very common. In fact, it's so common that it is part of any kind of the scaffolding tools that we know for a whole bunch of frameworks, including JHipster, Play, and Grails on the JVM. This is a very pervasive model. Now, if we look at our layered architecture, and if we have different large functional areas in our software, let's say the customer management and invoicing and payments, then in theory it looks like something like this. Unfortunately, in the practical side of things, as we start to get some requirements and things start to have to be implemented that aren't that clean, we start to grow towards a model where we quickly use a little bit of that service, or I'll just talk to that to that repository over there to fetch that information, and I'll recombine it like that, and it becomes a little bit messy over time and rather difficult to understand as the application grows. So what can we do to remedy that? I think about 15 years ago, 14 or 15 years ago, Eric Evans had published this famous book called Domain-Driven Design. You have to look at it, if you haven't read it, with a bit of a historical perspective. Because being published in 2004, he's talking about this up-and-coming technology called XML, for example. So you kind of have to think about the historical context, but it contains a whole bunch of very good ideas that are still very applicable today. And one of those ideas is basically the aggregates and the aggregate root, where basically you look for a nicely cohesive bunch of functionality in your application that fits together and that has low coupling to the outside world, and that is basically your aggregate. And then you look at the entities that make up that piece of functionality, and you look at really the one entity where everything hangs off, and that's the aggregate root. And this is really a very nice way to start looking at how to divide things up, how to divide your application into logical pieces or modules. Now, when it comes to modules, at some point you'll need to have some interaction between them, some dependency. If you have some invoices, they'll need some information from a customer, or they'll need some things there. So how do we deal with those things? Well, the first thing to really look for is in which direction should the arrows flow, and how should I make them flow between my different modules there. So if I have my customer here, my invoices will, as I said, probably require some information from my customer. My payments will probably require some information from invoices, so we know what needs to get paid. Maybe we need some additional info from customer as well. What we really want to have is to build a graph like that with no cycles, so an acyclic dependency graph, where we have certain things that can produce change in others and others not. So what we really want to have is very stable concepts at the bottom that are really the foundation of our business, of our application, and then more volatile, unstable concepts at the top, so that the unstable ones depend on a stable foundation and not the other way around, to reduce the overall impact of changes and the overall churn when we want to start modifying things. So, module boundaries, as we briefly discussed already, you have to start looking for highly cohesive blocks of functionality within your application. This is something that should come with low coupling as well to other modules. I think it's easier said than done. It's an exercise that does take some thinking of how to isolate those things. You should look at what you can do to reduce the cognitive load to the outside. So look at what you can do to really expose a small, well-defined, stable API to the rest of the application outside of the module. And ideally, this should only revolve around the aggregate root, so that all the other entities and the rest of the implementation becomes something that is private to the module and not visible anywhere else, in order to reduce the cognitive load. And if you have interactions between modules, you should really look at only depending on the API of other modules and not the implementation, so that you basically end up with a situation like this, where one API can depend on another API, or an implementation can depend on another API, but you can never have something depend on the implementation of a different module directly. Now, when we want to put this into reality, when we want to isolate code, we have a spectrum of possibilities at our disposal. The simplest one is that we just have one module, one jar, and we have that's all kind of being built together in our build tool. It has the same version, it's part of the same application, and we just use a separate package to represent our modules. This works well for very simple systems, but at some point you may get to the point where just sticking everything in one package to keep things private with package private scope in Java may be too little for what you need. So the next step up is to really start looking at modules at the build tool level. This is quite interesting, because then you start to have a jar per module. You start to have enforcement of the acyclic dependency graph at the build tool level. You start to have class byte isolation enforced by the build tool as well. So this is quite a nice thing. If that for some reason isn't enough anymore for your needs, the next step up from that is to really move part of the code to a separate repository. You version it separately, and you then integrate it at the end like a library in your app. And then finally, if that is not enough, you can then pull all that out of the main application into a separate service that you can then deploy separately. So if you look at the spectrum of choices that we have here, and if we were to draw a line where co-located integrated systems or monoliths stop and microservices begin, it's pretty much there, where we have a whole array of choices on the monolith side of things. And then finally, once we've exhausted them all, we go to the microservices side. So I think the idea is always to start with the simplest thing that could possibly work for your context. And only once you reach the limit of that, do go to the next one. And again, look if that works for you or not. Again, if you have infrastructure components or if you have some internal libraries, the separate repository thing there is a great thing. Now, if we look at the two middle choices that we have there, the little bit of middle ground between the full services and full monolith, everything together, we have a couple of advantages that we can get from those. So we have, as we said, the compiled class path that is being restricted. We have the enforcement of the acyclic graph at the build tool level. We are able to partially rebuild the project. In Maven, we can specify, for example, the module, and also make dependence with the -AMD switch, and then we only build part of the project to kind of save time and make things go quicker without having to do everything. It's easy to see the forest from the trees by looking at auto-generated diagrams. IntelliJ does this very well. Just select your different Maven modules in a project, and I think it's Control-Shift-U, and it will give you a nice diagram of the dependencies between them and how your application really fits together at the high level. So this is really already a whole bunch of very powerful functionality that we get with relatively little change. One of the big problems that this doesn't solve is jar hell. So when you have transitive dependencies to conflicting versions of the same library. So how can you deal with those? I think the first step is really avoid the problem in the first place. If you can reduce the overall number of dependencies that you have, I think that already reduces the probability of something like that hitting. So if you really just need that one utility method in this Apache 2.0 license library, wouldn't it be easier to just copy it in your code base and instead of pulling in that entire dependency? Something to think about. I'm not saying you should always do it like that, but think about it as a possibility that could potentially be helpful in scenarios like this. Also, when choosing a library to solve a specific problem, aim for a library with 0 transitive dependencies. It makes your dependency graph much easier to understand and much more predictable over time. So this is something when evaluating libraries that you should definitely put in your evaluation criteria. Another nice thing you should definitely do on all projects is making sure that all dependencies across all modules of the different libraries is actually something that is enforced by your build tool to be the same everywhere, so that you do not have a different version of Spring in module 1 than module 2, for example, or common slang, or whatever you choose to use there. And if all these things fail, you still have the final possibility of shading if the conflicts are not resolvable. So shading is nothing else than just copying all the code from a library under your own namespace, so that instead of having org apache my library, you have mycompany.org.apache.mylibrary, where you have a parallel namespace, and then you can have multiple versions of the same library working together. So those are a bunch of possibilities at your disposal. If you want to do the dependency conversion, we talked about to enforce the same versions being used everywhere. It's just a small snippet that you need to copy in your Maven build with the Maven Enforcers plugin, and that already works for you. If you want to, on the other hand, start looking at enforcing the usage of packages, where we talked about with never using the implementation part of another module directly, you do have a bunch of possibilities. With Java 9, we have the module system with module-info.java that will help us there. But it will be, I think, no big surprise to most of you that very, very few people have moved into that direction yet. So if you aren't on Java 9, what can you do? Well, it turns out that with Java 8, you're not out of luck either. We have a bunch of good possibilities. There's this GitHub project, for example, called CodeAssert, and it lets you define a bunch of rules of how your code is allowed to access the different parts. So it's a little bit of a DSL. So you see we've got class, hello. which is basically representing a package.com.hello. And we have sub-packages as dependency rules, payment API, so that would be com.hello.payment.api. We've got payment impl, so com.hello.payment.impl, and invoice API. And then we define some rules that payment API is allowed to use the invoice API, and payment impl is allowed to use the payment API and the invoice API. We kind of load up the Maven structure of our project and start enforcing those rules with a dependency analyzer. This takes just a few milliseconds. You can run this as part of your regular test suite, and it allows you to detect those kind of violations in the rules that you have established for your architecture very, very quickly. So easy to implement and well worth it to avoid having things deteriorate over time and keeping it generally clean. But an application, of course, isn't very useful if it isn't persisting data somewhere. Some applications can live without, but the vast majority do need to have some kind of persistence. These days, relational databases still vastly dominate that market. So how can we deal with relational database in this case? Quick reminder, what do they provide us in terms of advantages? We've got referential integrity, very, very powerful to make sure that the data that we have in there is actually valid. And we have atomic transactions so that we can avoid all the problems of having to manually implement measures to deal with eventual consistency, and instead we get it for free as part of our database system. Now, if we have our modular application there, the first rule that we really have to stick to, because if we've nicely modularized the code, it would really be a shame to put everything back together at the database layer and give up the separation and the clear picture that we've established there. So the first thing should really be that each module only accesses its own tables or database objects. So that if we look at our database and we zoom in a little, the picture should actually look something like this, where we have for every module that we have at the top the equivalent set of database objects at the bottom, and every module only accesses its own set. So it means that there is no sharing of tables or objects between modules. And the most difficult part to implement that is actually joins. You do not want to join between modules. Why? Because you want to keep your options open. So if you're moving up on that spectrum of code isolation, at some point you deem that the co-located deployment, the integrated system isn't enough anymore for that module, you want to be able to pull it out into an independent service. And if you have joins at that level, it will be much, much more difficult to achieve. So try to not work with joins at that level. You can have ID references, that's fine. In your queries, just do not join against the table. Use the API for that and rework the API of your module and rework some of the queries to be able to deal with those. What you do not have to give up, though, is referential integrity. That is actually quite nice. You can still have referential integrity and transactions, because if you were to separate out a module later, you could just remove the foreign key relationship and then move that part of the data in its own separate persistence entity away from the rest of the database, and you would be perfectly fine. The rest would keep on working, so it wouldn't be a big loss for that, but you still can reap all the benefits until you need to do that. So our picture looks more like this, where we have our APIs of our different modules and their private implementation accessing their private subset of the data in the database. So in terms of isolating that data between modules, again, a spectrum of choices. The simplest one is that we have the same database technology, the same database, the same schema, and every module just has its own set of tables. That works up to a certain size of database, and then it becomes more complicated to kind of distinguish and avoid accidentally joining or using some object that does not belong to the own module. So we have a nice technology in databases, very well established, to do some name spacing. It's called schemas, and it allows you to basically logically group together a bunch of objects. So that's kind of the nice first step up from there. In case that's not enough, in case you've reached the limits of that, then you can start looking at still keeping the same database technology to have just one set of expertise that you need to manage in-house on the operations side, but then start moving out some of those schemas along with the modules when you go to separate services into their own separate databases as well. And if that is not enough, if the technology that you've used to underpin the persistence of your module isn't really appropriate for what you need there, you need to move to a vastly different type of persistence, like if you were to move to graph or to object databases or to any other technology, you can just then take the last step and move out of there. So you have a vast array of choices that you can use for that. Now, if you're dealing with a relational database, you'll need at some point to be managing the structure of those schemas and to be able to evolve it over time along with your application. So if you aren't, I highly recommend you to use a tool to do that right now. There's lots of mature options on the market to be able to help you with that. Do not do it manually. Just pick a tool that does the job. I do not want to influence your choice as to which tool you should take, but maybe use one there. And if you use Flyway, for example, or any other tool there, the first two options that we have on the spectrum there are really things that should be managed within the same life cycle, because we still have the foreign key relationships present there. We still have the referential integrity, so you should probably look as having one common life cycle for the database, even though the objects may be split across different schemas. Now, scaling is another big topic when it comes to microservices, often touted as one of the main advantages. So let's have a look at what we can do in terms of scaling and in terms of scaling up to start with. If you look at the offering on AWS these days, we have quite a wide range of options available in terms of instance sizes. On the low end, we have something like the T2 Nano, where we have one virtual CPU and half a gigabyte of RAM. And on the high end, we have something like the X1E 32X Large, where we have 128 CPUs and almost 4 terabytes of RAM. That's with a T, not with a G. So you kind of see the spectrum of choices that we have there. So you can have a long way before you exhaust the possibility of being able to scale up, especially because you're not limited to one instance. But if you need to scale your modular monolith beyond the size of that, you can also have multiple of those instances. But sometimes you do not want to scale the individual modules at the same rate. You have certain parts of your application that may demand more capacity than others. So how can you deal with those? Again, spectrum of choices. The first one is to assign different capacity to different modules with different executor services. So if you have, for example, here the payment and the invoice module, and you have a whole bunch of virtual CPUs available in your machine, then you can assign a higher number of threads on the one end to the module that requires more processing power and a lower number of threads to the other, to subdivide that capacity along module boundaries in a way that makes sense for your application. Now, that's not the only option, of course. It's very well possible that this is not enough, or you need to start looking at asynchronous communication between modules. So what do you have at your disposal there? Well, an often overlooked solution there is to use your relational database as a queue for having communication between modules. So how does this work? Well, let's say we have a simple table here for our queue where we have an ID for a message and a payload for the message. If you want to add something to that, you would just insert into that queuing table. You would add a new message, the ID would get auto-assigned, and you would be able to post messages to that queue. And if you actually want to consume something from that queue, here, for example, with Postgres, you could do something like this, where you issue a delete statement against the queue to remove an item from the queue. Which item do you select? Well, you select one item for update, so you're going to try to lock it from the top of that queue. But if it is already locked by some other consumer somewhere, we have the skip locked clause that will say, do not wait for that item to be released, go straight to the next one. And so if you have 3 clients blocking the first 3 items, we don't need to wait. Our client will go and select the 4th one. And once we have selected that, we also return the message. So how does this work in practice? I open a transaction. I issue this statement against the database. So I delete the record, but get a result set back at the same time containing the payload of the message. I perform whatever work I need to do, and then I either commit or roll back the transaction. What happens if I commit? Well, my work gets committed, and at the same time, as part of the same transaction within the same database, the delete gets committed as well, and that message is being removed atomically from the queue. If, on the other hand, something goes wrong, there is an exception, then a rollback is being triggered, my changes in my code are being rolled back, and so is the delete here, and the message automatically ends back in the queue. So this is actually a very powerful mechanism when you're not dealing with super high loads to have nice consistency between the queue and the rest of the data of the application. So this is also an option well worth considering when you're dealing with asynchronous communication between modules. And if that's not a possibility at all for you, then because you've reached, for example, the capacity limits of your database, or it's generating too much churn on certain underlying storage, for example, then you can look at moving to a dedicated queuing system where you can deal with very, very high capacity as far as that's concerned, and then you can really start pumping out your messages there and really reading them back as part of the same application. There is no rule that says that it can be the same application consuming them as well, just a different module. Now, language independence is something that is often spoken about as well when we talk about microservices, where you really want to have something that you want to pick the best technology for every individual service. You want to make sure that you've got the most appropriate thing there. So how do you deal with that if everything is just running together on the same underlying platform? Well, it turns out that we actually have quite a good situation on the JVM, because if you look at the language landscape that you have today and the level of interoperability that we have between those languages, then it's actually looking pretty good, because even though we have things like Scala and JRuby and a few others that can easily consume Java, but not the other way around, we then have options like Groovy and Kotlin where two-way interop is actually working quite well. So this is quite a powerful thing that we have at our disposal there on the JVM, and there's actually even more languages than these that you can have there. So you really have a very strong possibility to write every module in the most appropriate language for that module. Now, small shameless plug. What do I do with my company? We provide two software products on the market. So one is Boxfuse, which is a way to deploy your applications on the AWS cloud with just one command. So if you're looking to focus on development and not spend too much time with ops, this could be a good way for you to deal with that. And the other product that we have is Flyway, which I briefly mentioned before. Some of you may be using it already. It's quite popular. I think the main point with Flyway is that you can finally start to have a clean way to evolve the schema of your relational database over time. So it's an Apache 2 licensed project. You can just pull in the dependency, and it helps you drop in SQL files that mirror the evolution of the expectations of your database over time. So if in our case here, our modules in version 1 do require some tables to be present, and in version 2 of our application, we have additional columns or additional views or additional tables that are required. We do need to make those changes across all environments, and Flyway helps you just create one SQL file, and it will automatically, if you integrate it with the API, deploy your application. It will, at startup of your application, evolve your database like you need to be. So it supports a wide range of databases, It's very wide usage in the industry. It's been built for continuous deployment from the start, so it integrates quite nicely with those models. And we have a community edition as well as a pro and enterprise edition. So if we were to summarize everything that we saw today, I think having a bit of a combination of some of the nice, simple aspects that we have at the low end with monoliths, and having having some of the clear organizational benefits of microservices and bringing them together, also for organizations that aren't IT giants, but are maybe at a more humble size, does provide you with a really, really good pragmatic choice for your company so that you can really be very productive without a lot of the runtime overhead that would be typically part of a fully blown microservices architecture. So I think this is really something for you to take back to your company, to maybe reflect on with your colleagues and see if this could be a good fit or not for some of the problems that you're tackling, or if at least part of those solutions or the spectrum of choices that we talked about before in the different areas we tackle could be worth visiting for you. So if we were to summarize that again in one sentence, I would say go modular and make your monolith majestic again. Thank you very much for your time. Terribly sorry about the problems in the beginning, and have a great evening. Enjoy the beers. Thank you. Now, don't forget to rate the talk, and if anybody is interested, I have some Flyway and some Boxfuse stickers if you want to pimp your laptops. Otherwise, thank you very much again for coming.